So last lesson we looked at inverse functions. We looked at creating inverse functions. We talked about the idea that not an inverse function doesn't, sometimes needs to be defined carefully in order to exist, I suppose, by making sure that the domain of the inverse matches the range of the inverse matches the domain of the function. I'm just going to summarize a little bit and sort of give you a little bit more detail there in this first sheet here we've got here. What I finished with last lesson was saying that any function can have an inverse. That's still true. And if you modify the range to match the domain of the function, that'll give you an inverse. That's still true. But when we're looking at an inverse function, okay, so we're now going from relations to functions, then there's some conditions that need to be met in order for the inverse function to exist. Or it's probably a better way to write it is, in order for a function to have an inverse, certain things need to be met. That's probably a better way of writing it. In order for a function to have an inverse, certain conditions must be met. Number one is that f must be 1-to-1. We have talked about this. This is why I asked you to start looking at functions and categorizing them as 1-to-1 or not, because I knew inverses were coming up. In all functions, it is a condition for a function to have an inverse that it must be 1-to-1. And an easy way of thinking about that is that it must pass a horizontal line test. A horizontal line test, not a vertical line test. That's just to determine whether it's a function at all. A horizontal line test must also be passed in order for it to have an inverse. And then the other thing that must also be necessary for it to be an inverse is that the domain of the function must be the same as the range of its inverse, and the domain of the inverse must be the same as the range of the function. Okay, we've kind of settled on this bit. We've looked at this bit before, that the domain of the inverse must match up with the the top one, beg your pardon. We've settled on the top one before, that the domain of the function must be the same as the range of the function, but we haven't sort of looked at this one as well. So all of these things must match up. If these things are true, then it will have an inverse. Note, not a subset. The domain must be the same as the range, not just a subset of it. Just really quickly, I'm going to go back to this graph a few times. So we can sort of see here that if I have y equals x squared, that's your old classic parabola shape there. If I go to x equals y squared, I know I showed you this before, it goes on its side, right? So when I switch the inputs and outputs over, and we can see that this here, whilst the rule works, it's the inverse, the red line's the inverse, the red line fails the vertical line test, right? So it's a relation, but it's not a function because it fails the vertical line test. So I hope it's not too much of a expansion on your brain to think that if I go backwards, the failure of a vertical line test in the inverse would mean that it's failing a horizontal line test in the original function. That's the link between the two. By the way, this graph hasn't just fallen on its side too. This is so hard to articulate via video, so I'm just going to use my hand here. But you can sort of see that the reflection is like that. So this part of the function ends up being down here, and this part of the function is up here. So that bit has flipped to there, and this bit has flipped to there. Sorry for the video watchers, you won't see what I'm doing with my hand there. So just be mindful of that. That's how the flip works. It's reflected over that diagonal line. So if we sort of look at the y equals the square root of x, that's that purple line there. It's just that part there. So what we will need to do in order to get that purple line to be the reflection of this is we're going to have to restrict the domain of the original function. So rather than having y equals x squared, I'll turn that one on, I'll leave it on. Instead of having y equals x squared, I'm going to restrict the domain to say x is greater than or equal to 0. And now, can you sort of see that this black line now does reflect onto the purple one? So this is now behaving as a good function and its inverse. This bit gets reflected over the diagonal to make the purple one. The black one is now reflected. Only possible if we restrict the domain of the original function to start with. I could have restricted it differently. I could have gone less than or equal to 0. That would be okay. But then I would have to make this minus the square root of x. And now that's a reflection as well. That's also an appropriate function with its inverse. But the domain is different here. And the function that comes out to be its inverse is different as well. Okay, does that kind of make sense? Okay, moving on then. So, next bit of notes to write down. Actually, I'll zoom out now, but I'll get to the example in a second. So if f does not satisfy these conditions, its domain may be restricted until it does. And that's exactly what I was talking about when I was showing you stuff. So I'm looking at the example on slide 19 now. I'm trying to be really quick here. And you can see that if I have f of x equals x minus 2 all squared plus 1, that's just a parabola example again, but I've translated it by 2 units to the right and 1 unit up, okay, just using our standard translations. So I've got f of x equals x minus 2 all squared plus 1, and I've started with f kind of in inverted commas being unrestricted. In other words, it's got an implied domain of all real numbers, because I haven't said explicitly what the domain is. So the implied domain is all real numbers. And I want to actually specify the domain now in order to make it a invertible function. So at the moment, it's unrestricted, and so it looks like this. Okay? Now, take it as read, please. You could do it yourself, but if you use the usual techniques that we practiced last lesson in order to find the inverse, that would be the inverse here. F of minus 1 equals x minus 1, or the square root of x minus 1 plus 2. So you can see for f of x, I can draw a red line somewhere on this graph and a horizontal red line like I've got here, and so it fails the horizontal line test. So as it stands right now, it is not going to be invertible as it stands. Okay? It's not invertible as it stands. However, if we define f going from 2 to infinity, that's its domain. In other words, what I've done is I've looked at this graph and I've gone, well, the turning point here is 2 comma negative 1, so 2 comma 1, 2 comma 1 here. So what I'm going to do is rather than carve out the whole graph, I'm going to start at the turning point, which means everything from here on will be 1 to 1. Okay, because I'm not going to consider before the turning point. It's only either side of the turning point that the graph stops being 1 to 1. From the turning point onwards, it's 1 to 1. So if we define the function as going from and including 2 all the way to infinity, and what does that mean? Well, that means that its range is going from 1, the other turning point coordinate, to infinity. Then giving you a chance to catch up. Then we can draw out that domain range table in the following way. I might even just change colors just so you can sort of see it happening as we go along. So I can say that the domain of f is 2 to infinity. I can say the range is 1 to infinity. And then the range I know needs to be, the range of the inverse needs to be 2 to infinity as well. Needs to be the same. And I'm going to underline that in red so you can sort of see it. And what does that mean about the domain of the inverse? So that it's fully defined, both the function and its domain. Well, if I just do what I did with composite functions, and that is, oops, I've missed a number there, haven't I? 2 to infinity. If I do what I did with composite functions, and that is substitute the endpoints of the range in for y and solve and see what I get, you're going to get what I think is a very unsurprising result. So instead of y, I'm going to put 2. So I've got 2 is equal to the square root of x minus 1 plus 2. So that's just f minus 1. That's the inverse function. If I then subtract 2 from both sides, I get 0 is equal to the square root of x minus 1. If I then square both sides, the square of 0 is 0, so I get x minus 1. And then if I add 1 to both sides, I get x equal to 1. In other words, my endpoint is going to be 1, comma, to infinity. And I've got an obs there because if I'm reflecting my inputs and my outputs, then clearly this range is going to meet with this domain. As long as I've defined my range really carefully and haven't just put an R there for all real numbers, as long as my range precisely describes what f is mapping to, then these two are going to have to match. They have to. Okay? So these two match, and so that's the function that will map to my inverse function. Okay, real brief. If I go back to the inverse relations, then you can see here that's what I've got. I'll turn these off so you can see it. There's one more I have to turn off. Where haven't I turned it off? So here is y equals x minus 2 all squared plus 1, but I've restricted it from the turning point, like so. If I then tick this one, it's now inverting nicely. This is a reflection of this. This swings around the y equals x line to form the green line as it inverses. And yes, I could, if I wanted to, I could have chosen, I should have said less than or equal to be honest. I could have chosen this, but then when I find the inverse, I would have to change my inverse function accordingly. So generally speaking, it's a generally reasonable practice to sort of take the right-hand side rather than the left-hand side when you're cutting out parts of the function to make it one-to-one. So that's why I kept the positive side, and it seems to flow through much more nicely if we do that in terms of an inverse. Okay, any questions on that? Got to ask quick because I need to move on pretty quick. Okay, the other thing I wanted to talk to you about was points of intersection. Now, a point of intersection, you can write those notes down. I'll zoom up so you can see them. But again, I won't give you too much time to write it down. Oh, sorry. Points of intersection are like so. We should know by now what a point of intersection is. A point of intersection is where two lines cross over on a graph. It makes a point of intersection. To be more precise, it's the pair of coordinates that satisfy both equations. That's why it's sometimes called a simultaneous equation. It's the pair of coordinates that satisfy both functions. Okay, so that's basically a reminder of what points of intersection are. And I'll give you just a quick chance to write that down, but you'll see this in action. But because we reflect across y equals x, because that's our reflection, the point of intersection is always found on this line. Could be more than one point of intersection. It's always found on this line. To find the point of intersection, we set f of x equal to x, or the inverse function equal to x, and then solve whatever is easiest. Now, I'll be zooming out in a second, so you'll have more chance to write this down in a moment, but I'll just go back to here and just see it in action. You can see it here. The point of intersection is bang smack on the line here. y equals x. And if you think about it, it kind of makes sense why, I hope. Similarly for the square relations, I'll just have to redo it so I can get it working for us. Turn that one off and that one off. Sorry, so similarly for the square and the square root, once we've restricted it, of course, there's a point of intersection there and there's a point of intersection there. They exist on the x equals y line for what I hope is fairly intuitive reasons, reasonable reasons. Okay, so I'm going to go through an example and then that will do for points of intersection, and then we're going to move on to something else. So I'm not giving any practice time for this. Oh, sorry, I'll leave it zoomed out. So in our previous example, we had f of x equals x minus 2 all squared plus 1, and f to the minus 1, the inverse of f of x, equals root x minus 1 plus 2 for the given domain and range. I'm not going to write those down. For the given domain and range, which makes them invertible. So to work out the point of intersection, we take one of these and we set it equal to x, because we also know it's the point of intersection is also going to be a point of intersection with y equals x. So we can just set the equation equal to x and solve for x. Now, why did I choose this one? Well, I'm kind of thinking ahead, and this is where, like, as a level 4 student, that's what you need to be doing more and more. Like, thinking ahead, when I'm solving this, I know I'm going to be squaring to get rid of the x, to get rid of the square root, and that feels better than square rooting, I think. You could have chosen either, and you would get the answer eventually, but this is the way I chose. Maybe the other way is better, but I think this is a better way of doing it. So I'll just do a quick solve of this, just so you're right with it. So I might choose a darker colour so you can see it. So we've got the square root of x minus 1 is equal to x minus 2. So I just took 2 away from both sides. Square both sides to get x minus 1 equals... Now I'm just going to do the expansion rather than do it in 2 steps. So the expansion of x minus 2 all squared is x squared minus 4x plus 4. Okay, that's just x minus 2 all squared, right? So I've expanded that. Then I'm just going to bring everything over onto one side of the equation so that I can use my usual methods in order to solve. So I'm going to add subtract x and add 1. So I'll get 0 over here. I'll get x squared minus 5x, because minus 4 minus 1 is minus 5, and plus 1 will give me a plus 5 here as well. So that's my equation here. It's a trinomial, set equal to 0. So I'd go through my usual methods in order to work out what x is. Is it easily factorizable? No. I can't think of two numbers that will multiply together to give me 5 that will add together to give me minus 5. So it's not easily factorizable. Can I complete the square? Yeah, but there's an odd number in the middle. I'll be dealing with fractions. I don't want to deal with no stinking fractions, so I'm not going to use completing the square. So I can't easily factorize it. I can't easily complete the square. So I'm going to go straight to quadratic formula. And the quadratic formula is basically, if you remember, I match up the A's, B's, and C's. So A is 1, B is minus 5, C is 5. And then away I go into the formula. So therefore, x is equal to negative b. So b is negative 5. So negative 5, negative 5 is 5. Plus or minus the square root of b squared, which is 25, minus 4 times a, which is 1, times c, which is 5. Like so. All over 2a. A is 1, so it's just all over 2. Okay, simplifying that, I'll get 5 plus or minus the square root of 5 all over 2, which equals, this is the thing to be careful of, which equals 5 plus the square root of 5 over 2. I literally went to my calculator to make sure of this, so I won't waste time by doing the calculator operations. So I went to my calculator and noted that 5 plus root 5 over 2 is the only solution, because x has to be greater than 2, right? Because that's part of the conditions of the function and its inverse. X couldn't be 1 because then it wouldn't be part of the other function. So it couldn't be below 2, sorry, because it wouldn't be part of the other function. I'll show you that in a second. And then the other nice thing is that normally when you're doing a point of intersection, then you have to take the value and substitute it in for x to work out what y is. But because the point of intersection is on xy, on x equals y, sorry, then we can go straight away that's 5 plus root 5 on 2. And then the y is exactly the same, and it always will be. Always the same. Okay? So once you've worked out x, you've worked out y. So it's all done. So I'm going to go back to the graph just for a ticky and just show you this all matches up. So with these two here, like so, we can see that the point of intersection crosses over on the x-axis, and it crosses over at 3.618, 3.618, which would be 5 plus the square root of 5 divided by 2, 3.618. Okay, so that's what I'm saying. You could use your calculator to confirm that, but that's that point of intersection there. You can see that the other possible value, which was 5 minus the square root of 5, would kind of be down here somewhere if these graphs continued. But if they continue, well, like that and like that, but if they continued, these two functions would not be inverses of each other, because if I continued this one, for example, then it would flip over this way, and therefore it wouldn't be a function. It would be a relation, but it would be a function. So the two relations have 2 points of intersection, but the function only has 1 point of intersection because we had to restrict the domain so that it was 1-to-1. All right, last chance for questions before I move on. Okay.